In the spring of 2023, an automated monitoring buoy, anchored in the northeast Atlantic, approximately 500 kilometers off the coast of Portugal, transmitted a sea surface temperature reading to the NOAA data archive that caused the receiving system's quality control algorithm to flag the data point as a possible sensor malfunction. The algorithm was designed to catch errors. Temperature readings that fall more than 4 standard deviations outside the expected range for that location and that date are automatically flagged. They are not deleted, they are marked as suspect and set aside for human review. The system assumes, reasonably, that an instrument reading 4 standard deviations from normal is more likely malfunctioning than correct. The buoy was not malfunctioning. The ocean off Portugal that day was genuinely running at temperatures that fell more than 4 standard deviations outside the entire historical record for that location in April. The data point was confirmed, filed, and quietly noted by the researchers who monitor global sea surface temperature anomalies as part of their routine scientific work. Noted not because it was alarming in isolation, but because it was one of dozens of similar anomaly flags appearing simultaneously across the North Atlantic. Within weeks, climate scientists were publishing analyses of what was happening. The North Atlantic sea surface temperature anomaly that emerged in the spring of 2023 was, by the time it was fully characterized, the largest and most extreme marine heatwave ever recorded in the North Atlantic in the instrumental era. But the North Atlantic is not the subject of this documentary. I am telling you about Portugal in the spring of 2023 because of what it represents. Not a local anomaly, not a regional aberration, a signal. The leading edge of a global oceanic transformation whose center of gravity lies not in the Atlantic at all, but in the largest body of water on this planet. The Pacific Ocean covers 165 million square kilometers. It holds more water than all the land on Earth's surface would cover if the continents were assembled into a single basin. It connects the Arctic to the Antarctic along a north-south span of 15,500 kilometers. Its deepest point, the Challenger Deep, at the bottom of the Mariana Trench, is 11,034 meters below the surface, deep enough to submerge Mount Everest, with more than 2 kilometers of water to spare. And right now, in 2026, it is doing something that no instrument, no model, and no historical precedent has fully prepared us to understand. The Pacific Ocean is accumulating heat at a rate and in a configuration that has no analogue in the observational record. This is not a statement about global average temperatures, though those are also at record levels. This is a statement about the specific, localized, vertically extensive warming that Argo float profiles, satellite altimetry, and NOAA buoy networks are documenting in real time in the Pacific Basin. The warming is not uniform. It is not a simple background warming of the entire ocean surface. It has structure, it has geometry. It is concentrated in specific regions, at specific depths, in patterns that oceanographers recognize as having dynamical significance, meaning that the patterns are not passive. They are connected to the atmospheric circulation above the ocean through feedbacks that drive weather systems, generate storms, redirect rainfall, and ultimately determine where crops grow and where they don't across the largest land masses on Earth. We are going to walk through all of it. The mechanism, the history, the current measurements, the cascading effects on weather systems and food security and fisheries, and the atmospheric rivers that determine whether California has water. But before we do, there is a single number I want you to hold in your mind. In 2023, the global ocean heat content, the total thermal energy stored in the world's oceans to a depth of 2,000 meters, set a new all-time record. It also set a new all-time record in 2022, and in 2021, and in 2020, and in 2019, and in every year going back further than that. The ocean has been breaking its own heat content record every single year for more than a decade. That sequence of consecutive record years is not a statistical quirk, it is a trend. And the Pacific, as the largest single contributor to that trend, is the engine at the center of it. Here is the number. The Pacific Ocean in 2023 absorbed approximately 14 zettajoules of heat, 14 with 21 zeros after it, in excess of the pre-industrial baseline for that year. For context, the total annual energy consumption of human civilization is approximately half a zettajoule. The Pacific absorbed, in a single year, the equivalent of 28 years of total human energy use in excess heat, beyond what it would have held in a stable pre-industrial climate. That heat is in the water. It is not disappearing. It is not radiating back to space on any timescale relevant to the next decade. It is in the ocean, moving through the ocean's circulation systems, surfacing in regions and at times governed by the physics of those circulation systems, and expressing itself in the weather patterns, the storm intensities, the fishery collapses, and the atmospheric anomalies that are already affecting hundreds of millions of people. We will come back to that number throughout this documentary. Because the scale of the heat, its sheer magnitude, is the foundation of everything that follows. There is one more piece of context before we go back to 2013 and the first blob, because it changes how you hear every number that follows. The ocean absorbs approximately 90% of the excess heat that the Earth's climate system is accumulating due to the enhanced greenhouse effect. Of the total heat imbalance at the top of the atmosphere, the difference between the incoming solar radiation and the outgoing thermal radiation that is trapped by greenhouse gases, 90 cents of every dollar, goes into the ocean. The atmosphere and the land surface split the remaining 10 cents. This means that the atmosphere, the system whose temperature we measure when we talk about global warming, is only showing us 1/10 of the actual warming of the climate system. The ocean is absorbing the rest. The ocean is, in effect, buying time. Every joule of heat that enters the deep ocean, rather than the atmosphere, is a joule that does not immediately express itself in rising air temperatures, intensified weather systems, and accelerating ice melt. But it is not disappearing. It is not leaving the climate system. It is in the ocean, stored at various depths, moving through the circulation systems, subject to eventual return to the surface. The ocean's heat storage capacity has given human civilization decades of buffering against the full atmospheric expression of greenhouse gas forcing. That buffer has a limit, and it has consequences. The consequences are what the Pacific is showing us right now, but first we need to go back to the moment that oceanographers first began to suspect that the Pacific was doing something fundamentally different, not just warming steadily. That moment arrived in 2013, in a patch of ocean roughly the size of Australia. In the autumn of 2013, Nicholas Bond, a research meteorologist at NOAA and the University of Washington, was examining sea surface temperature anomaly maps of the Northeast Pacific when he noticed something that did not fit any pattern he had encountered in his career. A large, roughly circular region of anomalously warm water had appeared in the Gulf of Alaska and the Northeast Pacific, centered at approximately 45 to 50 degrees north latitude, roughly 1,000 to 2,000 kilometers offshore. The anomaly was not extreme by later standards, about 2 to 3 degrees Celsius above normal, but its size was extraordinary. It covered an area of approximately 4 million square kilometers, and it showed no sign of dissipating. Bond, in an interview that year, gave the anomaly a name that stuck. He called it the blob. The blob persisted and expanded through 2014 and into 2015. By its peak in 2015, it covered a region of the Northeast Pacific larger than the entire continental United States and was running approximately 4 degrees Celsius above the historical average for those waters. 4 degrees above average, sustained over millions of square kilometers for 2 years. This was not within the range of natural variability that the historical record had documented. It was not an El Niño pattern, although an El Niño did develop in 2015 and interact with the blob in complex ways. It was not a known pattern of the Pacific decadal oscillation. It was something that existing frameworks did not fully explain, and it had consequences. The consequences were not subtle. They were catastrophic for the marine ecosystems that live in the Northeast Pacific, and they translated into economic and ecological impacts that are still being felt more than a decade later. The first consequence was a collapse of the base of the food web. Cold, nutrient-rich water from the deep Pacific is normally brought to the surface in the northeast Pacific through a combination of wind-driven upwelling and the mixing effects of storm systems. This upwelling delivers the nitrates, phosphates and silicates that phytoplankton, microscopic photosynthetic organisms that form the base of the marine food web, require to grow. When the surface water is anomalously warm and stable, the temperature gradient that drives upwelling weakens. The deep, cold, nutrient-rich water stays deep. The surface layer, warm and nutrient-poor, supports far less phytoplankton. The phytoplankton collapse propagated up the food chain with the efficiency of biological systems that have no alternative. Zooplankton that feed on phytoplankton declined. The small forage fish, anchovies, sardines, sandlance, krill, that feed on zooplankton declined. The larger fish, the seabirds, the marine mammals that depend on those forage fish declined. Salmon returns to Pacific coast rivers in 2015 and 2016 were catastrophically low. The Chinook salmon returns to the Sacramento River in California were among the worst ever recorded. The commercial salmon fishing season was closed or severely restricted in multiple years along the Pacific coast. Fishing communities from Alaska to California felt the economic consequences directly. Seabird die-offs were recorded across the northeast Pacific at scales that alarmed researchers. Common murres, a seabird species that forages by diving for small fish, died in the hundreds of thousands along the Pacific coast between 2015 and 2016 in what became known as the largest recorded seabird die-off in North American history. The birds were starving. The fish they depended on were not there because the food web below the fish had collapsed, because the nutrient upwelling had been suppressed, because the water was warm. Harmful algal blooms, fed by the warm and stratified surface layer, proliferated across the northeast Pacific coast. The 2015 bloom of Pseudonitschia, a diatom that produces domoic acid, a neurotoxin, extended from California to Alaska and was the largest toxic algal bloom ever recorded along the Pacific coast. It forced the closure of razor clam fisheries, Dungeness crab fisheries and rock crab fisheries along hundreds of kilometers of coastline. The economic losses to the fishing industry were measured in hundreds of millions of dollars. The blob also affected the atmosphere above it. Anomalously warm sea surface temperatures in the northeast Pacific amplified the atmospheric ridge that had been sitting over the region, a semi-permanent high-pressure system whose abnormal persistence was linked to the warm water below it. That ridge deflected the storm track northward, away from California. Precipitation that would normally fall on the Sierra Nevada mountains and refill the state's reservoirs and snowpack was routed to Alaska and British Columbia instead. California experienced its worst multi-year drought in recorded history during the blob years. The 2012 to 2016 drought reduced Sierra Nevada snowpack to record low levels, forced mandatory water restrictions across the state, killed more than 100 million trees in the Sierra Nevada and other California forests, and cost the agricultural sector billions of dollars annually. The blob did not cause the California drought by itself. The drought had multiple contributing factors, but the blob's influence on the atmospheric ridge over the northeast Pacific was a significant and well-documented contributor to the drought's severity and persistence. The blob did not cause the California drought by itself. The drought had multiple contributing factors, but the blob's influence on the atmospheric ridge over the northeast Pacific was a significant and well-documented contributor to the drought's severity and persistence. The atmospheric ridge that the blob sustained has a name in the meteorological literature. Researchers studying the large-scale circulation pattern over the northeast Pacific in 2013 to 2015 called it the ridiculously resilient ridge, a term coined by Stanford climate scientist Daniel Swain that captures both the unusual persistence of the high-pressure system and the lack of any mechanism in the historical record for explaining how it maintained itself for so long. The ridge was not simply a weather pattern that happened to persist. It was a weather pattern that was continuously reinforced by the warm ocean below it. The ocean heated the air. The heated air reinforced the ridge. The ridge deflected the storms. The deflected storms did not cool the ocean. The ocean stayed warm. The cycle was self-sustaining in a way that ordinary high-pressure ridges are not. This feedback between ocean temperature and atmospheric circulation, the ocean warming the atmosphere reorganizing to maintain conditions that keep the ocean warm, is one of the most important dynamics in Pacific climate science. It is called ocean-atmosphere coupling, and it operates across a range of timescales from weeks to decades. The blob was a demonstration of what this coupling looks like at regional scale over a period of years. The Pacific Decadal Oscillation, the PDO, is the multi-decadal expression of this same coupling operating at the basin scale. The PDO is a pattern of sea surface temperature variability in the North Pacific that alternates between positive and negative phases on timescales of 20 to 30 years. During positive PDO phases, the Northeast Pacific is anomalously warm and the Central Pacific is relatively cool. During negative PDO phases, the pattern reverses. The PDO was in a negative phase from approximately 1998 to 2014, a period during which the Northeast Pacific was generally cooler than average and global surface temperature warming appeared to slow relative to the preceding decades, a period that climate contrarians sometimes called the global warming hiatus. The PDO phase transition that began in 2014 brought the PDO to a strongly positive phase, contributing to the warming of the Northeast Pacific that created the conditions for the blob. The current PDO state is strongly positive, more strongly positive than any comparable period since the 1980s. The positive PDO is not the cause of the Pacific's current anomalous heat content, but it is a component of the configuration that makes the Northeast Pacific particularly warm and that reinforces the atmospheric patterns that maintain and extend the warm conditions. And then in 2016 and 2017, the blob dissipated. The El Niño of 2015 to 2016 brought above normal rainfall to California. The Northeast Pacific cooled toward more normal conditions. The crisis appeared to have passed, but the scientists who had studied the blob most carefully were not reassured. They had documented what an anomalous Pacific warm event looked like. They had traced its consequences through the marine food web and into the atmosphere, and they had not found a satisfying explanation for why it had formed in the first place, not an explanation that accounted for its scale and duration within the bounds of natural variability. In 2019, a second anomalous warm patch appeared in the Northeast Pacific. Researchers called it Blob 2.0. It was not as extreme as the original blob in sea surface temperature magnitude, but its depth structure, the way the warming extended below the surface into the subsurface layers, was more extensive than the original event. The Argo float network, which by 2019 had substantially expanded its coverage of the Pacific, revealed subsurface temperature anomalies that the surface measurements alone had not fully captured. Blob 2.0 drove another round of fishery disruptions, another harmful algal bloom season, another period of disrupted atmospheric circulation over the Northeast Pacific. And it had not fully dissipated when the global oceanic heat content began its record-breaking acceleration in 2021, 2022, and into 2023. The blob was not an isolated event. It was not a statistical accident. It was the first clear expression of a Pacific Ocean that was changing in ways that the models had not fully anticipated, and that the historical record had not prepared us to recognize. What is happening in the Pacific right now is not Blob 3.0. It is something that contains the blob's dynamics as one component of a larger transformation, a transformation that is evident in every Argo float profile, every satellite altimetry pass, every NOAA buoy transmission coming out of the Pacific Basin. To understand what that transformation is, you need to understand how the Pacific Ocean normally works, the engine beneath the anomaly. The mechanism that, when it operates normally, keeps the Pacific's heat distribution in a state that the climate of the continents around it has been calibrated to for thousands of years. The Pacific Ocean is not a bathtub. This is the foundational misconception that makes ocean science difficult to communicate to a general audience. The intuitive image of the ocean, a basin of water with a surface temperature and a depth, misses everything that matters about how it actually works. The Pacific is a thermodynamic engine. It absorbs solar radiation at its surface, stores that energy at various depths, moves it horizontally through surface and subsurface currents, and releases it back to the atmosphere in patterns that are governed by the physics of fluid dynamics, thermodynamics, and the rotation of the Earth. It is a machine that drives the weather of every continent that borders it, and through the atmosphere, the weather of every continent that doesn't. The engine has components. Understanding those components is understanding why the anomaly we are currently seeing is so significant. The first component is the thermocline, below the warm, sun-heated surface layer of the Pacific, a layer that extends from the surface to depths of roughly 50 to 200 meters, depending on location and season. There is a region of rapid temperature decrease. This is the thermocline. Temperature drops from the warm surface values, sometimes 28 to 30 degrees Celsius in the equatorial Pacific, to the cold, deep ocean values of 2 to 4 degrees, and it does so over a depth range of perhaps 200 to 500 meters. The thermocline is the boundary between the shallow, warm, light water above and the cold, dense, dark water below. It is a stable boundary, not easily disrupted by ordinary mixing, because warm water is less dense than cold water and naturally stratifies above it. The depth of the thermocline varies enormously across the Pacific. In the western equatorial Pacific, the warm pool of water that accumulates there under the influence of the trade winds can deepen the thermocline to 150 to 200 meters, a thick warm water lid over the cold, deep ocean. In the eastern equatorial Pacific, near the coast of South America, the thermocline is typically shallow, sometimes only 20 to 50 meters below the surface, which is why the equatorial upwelling there, driven by the trade winds, so easily brings cold, nutrient-rich deep water to the surface, and why El Niño conditions, which deepen the thermocline in the east, so dramatically affect the fisheries off Peru and Ecuador. Heat stored at 200 to 500 meters in the central Pacific does not drive atmospheric anomalies directly, but it does constitute a long-term subsidy to the surface layer. Over years to decades, this deep heat anomaly will influence the temperature of the waters that eventually reach the surface through upwelling, mixing, and ENSO-related thermocline tilting. It is the base of the problem, the committed warming, that the ocean will express over the coming decade, regardless of what happens at the surface in the short term. There is a fourth component of the Pacific heat engine that we have not yet addressed, and it is one of the most consequential for understanding the long-term trajectory of what is happening. It is the connection between the Pacific and the global ocean overturning circulation. The thermohaline circulation, sometimes called the global ocean conveyor belt, is the planetary-scale circulation system that moves deep, cold, dense water from the high-latitude Atlantic deep ocean formation zones through the deep basins of all the world's oceans, and eventually returns it to the surface, where it absorbs heat and nutrients before making the journey back to the sinking zones. The Pacific sits at the upwelling end of this circulation. The deep water that forms in the North Atlantic and the Southern Ocean eventually spreads through the deep Pacific, slowly upwelling over centuries and returning to the surface in the eastern tropical Pacific and the Southern Ocean. When this ancient deep water finally surfaces in the Pacific, it has been out of contact with the atmosphere for several hundred years. It is cold, dense, and rich in nutrients and dissolved carbon dioxide. The rate at which this upwelling occurs, how quickly the deep water returns to the surface, is one of the factors that governs how much heat the Pacific surface can absorb from the atmosphere. Faster upwelling of cold, deep water cools the surface, increases the temperature contrast between ocean and atmosphere, and drives more heat exchange. Slower upwelling means the surface layer warms more readily and equilibrates with the overlying atmosphere at a higher temperature. Research published in 2024 using a combination of radiocarbon, dating of deep water masses, and Argo-derived ocean circulation estimates suggest that the upwelling rate in the eastern tropical Pacific has been decreasing over the last 2 decades. The decrease is linked to changes in the wind-driven circulation and to changes in the density structure of the water column produced by freshwater input from melting ice in the Southern Ocean. If the upwelling rate is decreasing, if the cold, deep water is coming to the surface more slowly, then the Pacific surface layer's capacity to absorb and release heat to the deep ocean is also decreasing. The surface layer holds more heat, it warms more, the heat content of the upper ocean accumulates faster. This mechanism, a decrease in deep upwelling rate contributing to an acceleration of surface warming, is not yet definitively established in the observational record. The signal is there in the data, but its magnitude and the confidence interval around it are still being assessed. It is an active area of research. What is established is that the Pacific heat engine is not operating in the same way it operated 30 years ago. The distribution of heat through the water column, the rate of exchange between the surface layer and the deep ocean, and the coupling between the ocean and the overlying atmosphere are all changing in ways that are detectable in the data and that make the future of the Pacific's thermal state different from its past. The thermocline is the storage vault of the Pacific heat engine. The heat that the sun deposits in the surface layer does not accumulate indefinitely at the surface. Much of it is mixed downward, crossing the thermocline through processes of turbulent mixing, internal waves, and winter convection, and entering the deeper ocean where it is stored on timescales of decades to centuries. The rate at which heat crosses the thermocline and enters deep storage has increased as the ocean has warmed. More heat at the surface means more heat available to mix downward. More heat stored at depth means more heat that must eventually return to the surface and influence the climate above it, not on a human timescale of years, but on the longer timescales of oceanic overturning circulation. The second component of the Pacific heat engine is the trade wind system. The trade winds, steady easterly winds blowing across the tropical Pacific from east to west, are the primary driver of the Pacific's surface circulation. They push surface water westward, piling warm water up in the western Pacific and creating the Indo-Pacific Warm Pool, the largest reservoir of warm ocean water on the planet. As that warm water piles up, it depresses the thermocline in the west and tilts the thermocline across the entire equatorial Pacific, shallow in the east and deep in the west. The trade winds also drive equatorial upwelling along the equator, where the divergence of the surface flow, powered by the Coriolis effect, draws cold, nutrient-rich water from below into the photic zone and makes the equatorial Pacific one of the most biologically productive regions in the world's oceans. When the trade winds weaken, as they do periodically in the warm phase of ENSO, El Niño, the warm water that had been piled up in the west begins to flow eastward along the equator. The thermocline in the east deepens, the upwelling weakens, sea surface temperatures in the central and eastern Pacific rise. The warm anomaly propagates eastward along the equator in a feature called a Kelvin wave. The Kelvin wave is the third critical component of the Pacific heat engine, the one that is most directly relevant to what is happening in the Pacific right now. A Kelvin wave in the ocean is not like a wave you would see on the surface. It is a subsurface disturbance, a deepening of the thermocline that travels eastward along the equator at approximately 2 to 3 meters per second, guided by the Earth's Coriolis effect. It takes approximately 2 to 3 months for a Kelvin wave to cross the entire equatorial Pacific from west to east. When a Kelvin wave arrives at the eastern Pacific coast, at the coasts of Ecuador and Peru, it depresses the thermocline, suppresses the cold upwelling, and warms the sea surface. This is the direct physical mechanism that produces the warm SST anomalies associated with El Niño. The Kelvin wave is the carrier of the signal. The critical development in the Pacific right now, the one that the Argo float network and the NOAA TAO buoy array are documenting in subsurface temperature profiles across the equatorial Pacific, is that the subsurface heat content of the equatorial Pacific is at levels that have not been observed at this stage of the ANSO cycle before. The warm water is deeper and more extensive than any previous ENSO warm event at a comparable phase has shown. The Kelvin waves that have propagated across the equatorial Pacific in the last 8 months have been unusually large and have deposited unusually large amounts of heat in the subsurface of the eastern Pacific. This subsurface heat is not yet at the surface. It is below the thermocline, out of direct contact with the atmosphere, not yet driving atmospheric feedbacks. But it is there, in the data, visible in every Argo float profile from 120 degrees west to 90 degrees west longitude across the equatorial band. When the next ENSO warm event occurs, when the trade winds weaken and the thermocline tilts and the Kelvin waves carry warm water eastward, that subsurface heat will surface. And when it surfaces, it will enter the atmosphere in quantities that have no precedent in the observational record. The question that the ocean scientists who are watching this data most carefully are asking right now is not whether this will happen. The subsurface heat is there, the ENSO cycle will continue, the Kelvin waves will propagate, the heat will surface. The question is, what happens when it does? In December of 2022, the scientific consensus on what the global climate would do in 2023 was as well established as anything in the earth sciences can be. The ENSO forecast, the official prediction of whether El Niño or La Niña conditions would prevail in the tropical Pacific in 2023, showed a high probability of neutral to weak El Niño conditions developing by the middle of the year. The climate models used for seasonal forecasting agreed with each other to an unusual degree. The prediction was not controversial. The global average surface temperature in 2023 was expected to be warmer than recent years, consistent with the long-term warming trend, but within the range that the model ensemble projected as the normal distribution around the trend line. What happened in 2023 was not within that distribution. Global average surface temperatures in 2023 exceeded every previous year in the instrumental record by the largest single-year margin ever observed. The anomaly was not 0.1 or 0.2 degrees above the previous record. It was more than 0.15 degrees above 2016, which had previously held the record, and 2016 was a year in which one of the strongest El Niño events of the 20th and 21st century was peaking. The 2023 El Niño that developed was strong, but not as strong as 2015 to 2016, and yet the temperature anomaly produced by the 2023 event was larger. The El Niño contributed to the anomaly, but it did not account for all of it. The residual warming, the portion above and beyond what the model predicted, was concentrated in the oceans, and it was concentrated in the Pacific. The gap between what the models predicted and what actually happened, the model residual, in the technical language of climate science, was concentrated in the ocean heat content. The models had accurately simulated the atmospheric component of the warming. They had accurately captured the contribution of El Niño. What they had underestimated was the rate at which the Pacific Ocean was transferring stored deep heat to the surface layer. Several hypotheses were advanced to explain the residual. One hypothesis focused on the 2022 eruption of the Hunga Tonga Ha'apai underwater volcano, which injected an extraordinary amount of water vapor into the stratosphere, more than any eruption in the satellite era. Stratospheric water vapor is a greenhouse gas. Its injection by the Hunga Tonga eruption produced a transient additional warming effect on top of the long-term trend. A second hypothesis focused on the reduction in shipping emissions following the implementation of sulfur content regulations for marine fuel in 2020. Shipping emissions include sulfate aerosols, which reflect sunlight and produce a cooling effect. The reduction in those emissions may have removed a masking effect on the underlying warming trend, allowing the ocean to warm faster than it would have with pre-2020 aerosol loading. A third hypothesis, and the one that ocean scientists who study Pacific heat content find most compelling, is that the model residual reflects a genuine acceleration in ocean heat uptake that is not fully captured by the current generation of climate models. The acceleration is documented in the Argo float data, which now provides temperature profiles to 2,000-meter depth across the global ocean with unprecedented coverage. The data shows heat penetrating deeper, faster than the models simulate. The models were designed and validated against an ocean that, until recently, was changing more slowly. The processes that are now governing Pacific heat uptake and redistribution are operating at rates that are beyond the range of the training data the models were built on. This is not an unusual situation in the earth sciences. Models are approximations. They capture the dominant physics of the systems they simulate and produce skillful forecasts within the range of conditions they were built to represent. When the system moves outside that range, the model's predictive skill degrades. The Pacific Ocean in 2025 and 2026 is operating outside the range on which current models were built. The model residual, the gap between prediction and observation, is not uniformly distributed across the Pacific. It is concentrated in specific regions. The Argo float data allows researchers to map where the models are most wrong, and the map shows a consistent pattern. The models underestimate heat penetration below the thermocline in the western Pacific warm pool, and they underestimate the rate of heat surfacing in the central and eastern Pacific during transition from La Niña to El Niño conditions. Both of these model failures point to the same physical process. The downward mixing of heat across the thermocline is faster than the models simulate, and the upward return of that heat during ENSO warm phases is also faster and larger than the models simulate. The implication is uncomfortable. If the models are underestimating the rate of heat exchange across the thermocline, they are also underestimating the amount of heat that is currently in storage below the thermocline in the Pacific. And they may be underestimating what will happen when the next major El Niño cycle surfaces that stored heat. A 2024 study, published in Nature Climate Change, attempted to constrain the Pacific subsurface heat content from the Argo data more precisely than had been done before. The study found that the current Pacific subsurface heat content is substantially higher than any of the leading climate models project, not by a small margin, but by a margin that changes the risk assessment for the next major El Niño event in qualitative terms. The models are not wrong about the direction of the trend. The ocean is warming. That is not in dispute. The models are wrong about the magnitude of what is currently in the reservoir. This matters for a specific and practical reason that extends beyond academic accuracy in climate projections. The models used by national meteorological agencies to generate seasonal and multi-year climate forecasts are calibrated to the historical relationship between ENSO indices and regional weather outcomes. When a model predicts that an El Niño of a given intensity will produce a drought of a given severity over a given region, that prediction is based on the statistical relationship between ENSO intensity and regional outcomes as documented in the historical record. If the underlying Pacific heat content is substantially higher than any previous El Niño in the historical record, the statistical relationships on which the forecast is based may not capture the correct magnitude of the regional impact. A forecast model that predicts moderate drought over southern Africa based on an El Niño of moderate intensity may be using a calibration that was appropriate for the moderate El Niños of the historical record, but is not appropriate for a moderate El Niño developing from the current anomalously warm Pacific state. The practical consequence is that humanitarian response planning, agricultural production forecasts, and water management decisions made using the seasonal climate forecasts from these models may be systematically underestimating the risk. The World Meteorological Organization and the national meteorological agencies whose seasonal forecasts underpin humanitarian early warning systems are aware of this calibration challenge. Work is ongoing to assess the degree to which the current Pacific state requires recalibration of the ENSO impact relationships used in forecast systems. But this is a research problem that takes time to resolve, and the next major El Niño may arrive before the recalibration is complete. The models are wrong about the magnitude of what is currently in the reservoir, and the reservoir is what determines what the next expression of the Pacific heat engine looks like. We will come back to what that expression looks like in Act 8, but first, we need to look at what is happening in the Pacific right now, in the data that was transmitted to shore stations and satellites in the last 24 hours. There are approximately 3,800 Argo floats in the world's oceans right now. Each one is a cylinder approximately 2 meters long and 20 centimeters in diameter. It drifts passively with the ocean currents at a programmed parking depth of approximately 1,000 meters. Every 10 days, it inflates a bladder on its lower section, reducing its buoyancy and sinking to 2,000 meters. Then it deflates the bladder, ascends slowly to the surface, profiling temperature and salinity at every depth as it rises. At the surface, it transmits its data to a satellite. Then it descends again. The Argo program, a joint international effort involving more than 30 countries, has been operating in its current form since the early 2000s. The float distribution is designed to provide approximately one float per 3-degree latitude-longitude square across the global ocean. Coverage is not perfectly uniform. Some regions are more densely instrumented than others, but the global ocean is now being profiled to 2,000 meters depth, with a density and regularity that was simply impossible before the program existed. The Pacific component of the Argo network provides the most complete picture of the Pacific Ocean's thermal state ever assembled. What that picture shows in 2026 can be summarized in 3 specific findings from the most recent data synthesis. The first finding is that the depth-integrated heat content of the Pacific to 2,000 meters, the measure that accounts for heat stored throughout the water column rather than just at the surface, is at the highest level ever recorded by the Argo network. Not slightly above the previous record. More than one standard deviation above the previous record, which itself was set in 20. The heat is in the water, distributed through the water column, and it has been increasing continuously, with only minor seasonal fluctuations for the last 3 years. The second finding is the spatial pattern of the anomaly. The Argo data, when mapped, shows a specific configuration of positive heat content anomalies that oceanographers working on ENSO dynamics recognize as a specific and significant pattern. The anomalies are concentrated in 2 primary regions. The first is the Western Pacific warm pool, the region between roughly 150 degrees east longitude and the dateline at latitudes between 20 degrees north and south. The warm pool is deeper and warmer than any previous Argo snapshot has shown for this season. The second concentration of anomalous heat is in the subsurface of the central and eastern equatorial Pacific, the region east of the dateline, along the equatorial band, at depths of 100 to 300 meters. This is the subsurface reservoir that was discussed in the previous act. It is the heat that has been deposited below the thermocline by a sequence of downwelling Kelvin waves and that has not yet surfaced. The fact that both the Western Warm Pool Surface Reservoir and the Central Eastern Subsurface Reservoir are simultaneously at record or near record levels is what makes the current Pacific state unusual. Previous El Niño events drew down one of these reservoirs to fuel the warm phase. The current state suggests both are loaded simultaneously, which has implications for the amplitude of the next major warm event that the Argo community is still debating. The third finding from the most recent Argo synthesis is the depth structure of the anomaly in the Central Pacific. The warming is not confined to the upper thermocline layer, as it would be in a normal seasonal or ENSO-related warm event. It extends below the main thermocline in ways that indicate that heat has been crossing the thermocline at elevated rates, and that some portion of the anomaly is being stored at depths of 200 to 500 meters, depths that are not in direct communication with the surface on seasonal timescales. Heat stored at 200 to 500 meters in the Central Pacific does not drive atmospheric anomalies directly, but it does constitute a long-term subsidy to the surface layer. Over years to decades, this deep heat anomaly will influence the temperature of the waters that eventually reach the surface through upwelling, mixing, and ENSO-related thermocline tilting. It is the base of the problem, the committed warming that the ocean will express over the coming decade, regardless of what happens at the surface in the short term. The NOAA TAO Triton Buoy Array, a network of approximately 70 moored buoys anchored across the equatorial Pacific, measuring temperature, wind, and ocean currents at subsurface depths in real time, provides a complementary picture of the equatorial Pacific that updates every day. The TAO data for the last 30 days shows that the subsurface temperature anomalies in the eastern equatorial Pacific are persistently positive, warmer than normal, at depths of 50 to 200 meters. The anomalies are not concentrated in a single pulse, as a discrete Kelvin wave would be. They are a broad, diffuse warm region that occupies the full depth range of the thermocline in the eastern equatorial basin. This pattern is consistent with the cumulative effect of multiple downwelling Kelvin waves over the last 18 months, each one depositing a layer of warm water below the thermocline, building up the subsurface heat content incrementally. The satellite sea surface temperature data, available from both NOAA's Coastwatch product and the European Copernicus Marine Service, shows a surface picture that is broadly consistent with its subsurface data. The Central Pacific is running warm. The Eastern Pacific is in a state of elevated sea surface temperatures relative to the historical baseline. But the surface picture understates the full thermal state of the Pacific, because much of the anomaly is below the surface. The surface is the expression of what has already come up. The subsurface is the forecast for what is yet to come. We have not yet told you about La Niña. Because what happened in the most recent La Niña period, the period that according to every historical analogy should have cooled the Pacific, is the most important piece of the puzzle. And it is the most alarming. Between 2020 and 2020, the equatorial Pacific experienced a triple dip La Niña event, 3 consecutive years of La Niña conditions, the longest sustained La Niña episode since the 1970s. La Niña is the cold phase of ENSO. During La Niña, the trade winds intensify. They push warm surface water even further west, deepening the warm pool and tilting the thermocline steeply. Cold upwelling water dominates the central and eastern equatorial Pacific. Sea surface temperatures in the central Pacific drop below the historical average. The eastern Pacific is cold. La Niña events cool the planet, not dramatically, not permanently, but measurably. The global average surface temperature typically runs 0.1 to 0.2 degrees below the trend line during La Niña years. The cooling is temporary. When El Niño returns, the suppressed heat re-emerges. But La Niña is the natural counterbalance to El Niño in the ENSO cycle. The triple dip La Niña of 2020 to 2023 should have provided a significant cooling of the Pacific surface. In every previous triple dip La Niña in the instrumental record, the cooling in the equatorial Pacific central and eastern sectors was substantial, sea surface temperatures dropping 1 to 2 degrees below normal. This time, the cooling was minimal. The equatorial Pacific cooled relative to the preceding warm state, but not to the levels that the historical analogues predicted. The Central Pacific remained anomalously warm even at the peak of La Niña conditions. The Eastern Pacific, while cooler than El Niño conditions, did not return to the cold temperatures that previous La Niña events had produced. Scientists examining the Argo subsurface data from that period found the explanation in the water column. The subsurface heat content of the equatorial Pacific during the triple dip La Niña remained elevated throughout the event. The La Niña surface cooling suppressed warm water at the surface and recharged the western warm pool as expected. But the cumulative heat content of the water column, the integrated thermal energy from surface to 2,000 meters, did not decrease. It continued to rise even during the La Niña period. The ocean was cooling at the surface, while simultaneously accumulating more heat in its interior. This decoupling between surface cooling and subsurface heat content is not what the historical analogues predicted. To appreciate how significant this departure from historical behavior is, consider the analogy of a building with a central heating system and individual radiators in each room. Normally, when the thermostat is turned down, when the La Niña phase begins, the radiators cool, the rooms cool, and the boiler in the basement cycles to a lower output. The surface expression and the deep reservoir respond together. What happened during the triple dip La Niña is as if the radiators in the rooms cooled, surface temperatures dropped, meeting the La Niña criterion, while the boiler in the basement kept adding heat to the system at an accelerating rate. The surface was showing cold conditions. The thermal bank account was growing, not declining. The physical mechanism behind this decoupling is still being studied. The leading explanation involves a combination of factors: enhanced heat transfer from the atmosphere to the ocean during the La Niña period itself, as the stronger trade winds that characterize La Niña increase the ocean-atmosphere heat exchange over the western Pacific warm pool, reduced outgassing of ocean heat because the surface anomaly was cold. and possibly enhanced downward mixing of heat through the thermocline driven by the increased mechanical energy input from the stronger trade winds. None of these mechanisms individually is unprecedented. Their simultaneous operation at the magnitude observed during the triple-dip La Niña is what made the outcome unusual. The scientific community has been careful not to overinterpret the triple-dip La Niña as a definitive statement that La Niña has permanently lost its ability to discharge Pacific heat content. One exceptional event is a data point, not a trend. The next La Niña event will provide critical information about whether the decoupling behavior was a one-time occurrence or the beginning of a new regime. But the data from the triple-dip event changes the probability distribution that researchers use when thinking about what La Niña conditions mean for the Pacific's heat budget. The prior assumption that La Niña reliably discharges some of the accumulated El Niño heat, providing a reset toward cooler baseline conditions, is now qualified. The qualification is that under conditions of rapidly increasing total ocean heat content, the La Niña surface cooling may be decoupled from the underlying subsurface heat accumulation, and the apparent cooling may mask a continued deepening of the heat reservoir. This decoupling between surface cooling and subsurface heat content is not what the historical analogues predicted. In previous La Niña events, the cold surface conditions were accompanied by some drawdown of the subsurface heat content as the cold water descended. The heat content anomaly that had built up during El Niño was at least partially discharged during La Niña. In the triple-dip La Niña of 2020-23, this did not happen. The heat kept accumulating below the surface even as the surface showed cold conditions. The media reports during 2021 and 2022 described the La Niña as providing a cooling offset to long-term warming. The headlines were technically accurate in describing the surface signal. They did not capture what was happening below the surface. The ocean was not cooling in any depth-integrated sense. It was storing more heat below the layer visible to the atmosphere, setting up the conditions that would erupt in 2023. When the triple-dip La Niña ended in early 2023 and conditions began transitioning to El Niño, the heat that had been stored below the thermocline during the 3-year La Niña period began surfacing. The Kelvin waves propagating eastward across the equatorial Pacific were carrying not just the ordinary El Niño warming signal, but the accumulated subsurface surplus of 3 years of anomalously rapid heat uptake. The result was the 2023 global temperature record. The result was the extraordinary marine heat waves. The result was the North Atlantic anomaly that caused the Portuguese buoy to generate a data point that the quality control algorithm thought was a sensor error. The La Niña did not cool the Pacific. It hid the heat below the surface. And when the El Niño transition came, the hidden heat came with it. There is a scientific debate about whether the behavior of the 2020 to 2023 La Niña represents a new regime for ENSO, a state in which the cold phase of the cycle no longer effectively discharges the accumulated subsurface heat, or whether it was an unusual event within the existing variability of the system. This debate is not yet resolved. The data needed to distinguish between these interpretations will take additional years to accumulate. What is not in debate is what the Argo floats and the Teo buoys are showing right now. The subsurface heat content of the Pacific in 2026, even after the 2023 to 2024 El Niño partially discharged some of the accumulated anomaly, remains at unprecedented levels. The reservoir did not empty during El Niño as fully as historical analogues predicted. The reservoir did not discharge during La Niña. It is now moving into the next phase of the ENSO cycle with a starting state of anomalous heat content that no previous ENSO cycle has begun from. This is the moment I told you we would return to, the moment when the pattern becomes clear. Every cooling phase that should have reset the Pacific to something closer to baseline has instead left it warmer than before. Not slightly warmer, significantly warmer. By margins that are measurable in the data and that change the risk assessment for what comes next. The Pacific Ocean is not a regional phenomenon. This is the thing that people living in Chicago or Paris or Nairobi might not immediately grasp. The Pacific is separated from most of the world's major population centers by thousands of kilometers. It appears, on a map, as a body of water confined to one part of the planet. Its temperature anomalies seem like they should be the concern of people who live near it. California, Japan, Australia, Peru. This is wrong. The Pacific controls the atmospheric circulation of the entire planet through a set of mechanisms that link the ocean to the atmosphere across scales of thousands of kilometers and time scales of months to years. The most direct mechanism is the Walker circulation. The Walker circulation is a large-scale atmospheric circulation pattern in the tropics, driven by the temperature difference between the warm western Pacific and the cooler eastern Pacific. Warm sea surface temperatures in the western Pacific heat the overlying air, causing it to rise vigorously in deep convective thunderstorm systems, the most intense on the planet, concentrated in the Indo-Pacific warm pool region. This rising air flows eastward at high altitude, descends over the cooler eastern Pacific, flows westward along the surface as the trade winds, and completes the loop. The Walker circulation is the atmospheric expression of the Pacific heat engine. It connects the ocean to the atmosphere and drives rainfall patterns across the tropics and subtropics. When the Walker circulation is strong, during La Niña, rainfall is enhanced over the maritime continent, Indonesia, the Philippines, northern Australia, and parts of South Asia. Rainfall is suppressed over the central Pacific, Peru, and Ecuador. The subtropical jet streams shift. The monsoon systems of South Asia and East Africa are influenced. When the Walker circulation weakens during El Niño, the pattern reverses. Rainfall shifts eastward across the Pacific. Droughts develop over Indonesia, Australia, India, and parts of sub-Saharan Africa. Excessive rainfall occurs over Peru and Ecuador, flooding river systems and triggering landslides. California may receive above-average rainfall in some El Niño events. The 2015 to 2016 El Niño, one of the strongest in the instrumental record, produced droughts in southern Africa so severe that more than 40 million people faced food insecurity. It produced flooding in Peru that killed hundreds of people and displaced hundreds of thousands more. It contributed to the worst coral bleaching event in the history of the Great Barrier Reef. All of these impacts were geographically distant from the equatorial Pacific. They were the downstream atmospheric consequences of a sea surface temperature anomaly in the central and eastern Pacific. The Pacific in its current state, with anomalous subsurface heat content across the equatorial basin and an extraordinarily warm Indo-Pacific warm pool, is positioned to influence the Walker circulation in ways that will affect agricultural yields and water availability across the entire tropics. The specific impacts on food security are worth detailing, because food security is the consequence of Pacific variability that affects the most people. Southern Africa is one of the regions most vulnerable to El Niño-related drought. The agricultural systems of Zimbabwe, Zambia, Mozambique, Malawi, and South Africa depend heavily on the summer rainfall season, which is strongly influenced by ENSO. When El Niño conditions reduce rainfall across southern Africa during the summer growing season, maize yields, the staple food crop of the region, decline. The economic resilience to absorb those yield declines is limited in countries where food insecurity is already widespread. The 2023 to 2024 El Niño produced below normal rainfall across southern Africa during the 2023 to 2024 growing season, resulting in regional maize production deficits that triggered humanitarian response operations across multiple countries. The United Nations World Food Programme assessed that approximately 27 million people in southern Africa were experiencing food insecurity in early 2024, with El Niño cited as a significant contributing factor. India's monsoon system, which delivers approximately 70 to 80% of the country's annual rainfall in the June to September period, and sustains the agricultural production of 1.4 billion people, is sensitive to ENSO conditions. Strong El Niño events are associated with reduced monsoon rainfall over peninsular India and below normal agricultural production. The connection is not deterministic. Some El Niño years have normal Indian monsoons, but the statistical relationship is strong enough to drive significant forecast uncertainty and production risk in years when El Niño is active. Australia's agricultural regions in the interior, Wheat and sorghum producing areas in Queensland, New South Wales and Western Australia experienced their lowest rainfall during El Niño years. The 2019 to 2020 Australian drought, which preceded the catastrophic wildfire season that burned approximately 18.6 million hectares of Australian bush, was associated with a positive Indian Ocean dipole event and El Niño conditions that produced the driest spring on record for southeastern Australia. The coral reef systems of the tropical Pacific, including the Great Barrier Reef, the reefs of the Coral Triangle in Southeast Asia, and the coral systems of Hawaii and the Central Pacific, are acutely sensitive to sea surface temperature anomalies. Corals exist in a narrow thermal tolerance range. When temperatures exceed their tolerance threshold by even 1 to 2 degrees Celsius for a period of weeks, corals expel the symbiotic algae that provide them with nutrition and color in a process called bleaching. Extended bleaching leads to coral death. The Pacific's elevated sea surface temperatures in 2023, 2024, and extending into 2025 and 2026 have produced the most extensive and severe global coral bleaching event in recorded history. A bleaching event that began in 2023 was still ongoing in 2025, making it the fourth global bleaching event in the satellite era and the longest in duration. Multiple bleaching events over consecutive years do not allow reef systems to recover between events. The cumulative mortality is changing the species composition and ecological function of reef systems that took thousands of years to develop. The Pacific fisheries, among the most economically and nutritionally significant in the world, are responding to the thermal anomalies in ways that are disrupting supply chains for protein that hundreds of millions of people depend on. The global marine capture fisheries industry produces approximately 80 million metric tons of fish annually, with a market value exceeding $400 billion. The Pacific Basin accounts for approximately 50% of global marine capture production. The fisheries of the Pacific, from the Peruvian anchovy fishery, that is the world's largest single-species fishery by volume, to the pollock fisheries of Alaska, that supply the fish in fast food sandwiches across North America, to the tuna fisheries of the Central and Western Pacific, that supply the canned tuna consumed on every continent, are not peripheral industries. They are food security infrastructure for much of the planet. The Peruvian anchovy, Engraulis ringens, is the most extreme case. Peru and Chile together harvest 7 to 10 million metric tons of anchovy annually in the Humboldt Current upwelling system off the western coast of South America. These anchovies are processed into fish meal and fish oil that are used as feed inputs in aquaculture, poultry production, and pig farming worldwide. When El Niño conditions suppress the cold upwelling of the Humboldt Current, anchovy populations collapse. The 1997 to 1998 El Niño reduced anchovy production from roughly 10 million metric tons to under 2 million metric tons. The 2023 to 24 El Niño produced significant suppression of the Humboldt Current upwelling system. Peru closed its anchovy fishing season early in 2023, citing biomass assessments that showed population levels below the threshold for sustainable harvest. The closure affected global fish meal prices, which increased by 30 to 40% over the course of 2023 to 2024, increasing production costs for aquaculture operations globally. Pacific salmon populations, an iconic species with enormous ecological, cultural, and economic significance across the Pacific coast of North America and in Japan and Russia, have been severely impacted by the warm Pacific conditions. Salmon are cold water fish. Their spawning, migration, and marine residence patterns are calibrated to temperature ranges that have been disrupted by the warming Pacific. The returns of Chinook and coho salmon to rivers in California, Oregon, Washington, and Alaska have shown alarming declines. The Sacramento River Chinook Run, which supports a multi-million-dollar commercial fishing industry, was closed completely for the second consecutive year in 2023, the first back-to-back closure in history. The economic impact on fishing communities along the Pacific coast runs into hundreds of millions of dollars annually. The atmospheric river systems that deliver water to the western United States and have become increasingly volatile and intense in recent years are energized by the Pacific's thermal state. Atmospheric rivers are long, narrow plumes of concentrated water vapor in the atmosphere, fed by moisture evaporated from the warm Pacific surface. When they make landfall on the Pacific coast of North America, they can deliver extreme rainfall and snowfall that fills reservoirs and refreshes snowpack, but also produces flooding, landslides, and infrastructure damage. The record atmospheric river seasons that California experienced in the winters of 2022 to 2023 and 2023 to 2024, which ended the preceding drought at the cost of billions of dollars in flooding damage, were energized in part by anomalously warm Pacific sea surface temperatures that increased the moisture content of the atmospheric rivers to record levels. The Pacific is not a regional phenomenon, it is the climate of the world. The question that the ocean scientists who monitor Pacific heat content are now grappling with is not what happened in 2023. That event is documented and partially understood. The question is what happens over the next decade, given the current state of the Pacific's subsurface heat content. The Argo data provides the boundary condition. The Pacific water column is carrying more heat than it has at any previous time in the observational record. That heat is distributed through the depth range of 0 to 2,000 meters in a pattern that makes it available to influence the climate on timescales of years to a decade. It will not stay in the ocean forever. It will return to the surface through the processes of enso-cycling, upwelling, and the slow overturning circulation. When it does, it will influence the atmosphere. The specific scenario that multiple modeling groups have been examining is a major El Niño event initiated from the current anomalously high subsurface heat state. In a normal El Niño event, the warm anomaly that develops in the central and eastern Pacific represents the surfacing of heat that had accumulated in the western warm pool during the preceding La Niña. The heat in the warm pool is the fuel. The El Niño is the expression. In the current scenario, there are two separate reservoirs of anomalous heat that a major El Niño event could draw upon simultaneously. The first is the Indo-Pacific warm pool, which is deeper and warmer than at any previous El Niño onset in the observational record. The second is the anomalous subsurface heat in the central equatorial Pacific, the heat that did not fully discharge during the 2020 to 2023 La Niña period. A major El Niño event that draws down both reservoirs simultaneously, the surface warm pool and the subsurface anomaly, could produce sea surface temperature anomalies in the central and eastern Pacific that exceed anything the historical record contains. The magnitude of the atmospheric response to such an event, the strength of the Walker circulation weakening, the shift in rainfall patterns, the drought intensification in sensitive regions, the storm intensification in affected areas would scale with the magnitude of the sea surface temperature anomaly. An El Niño event that exceeds the 2015 to 2016 event in sea surface temperature magnitude, developing from a starting state where the tropical Pacific's heat content is already at record levels, would be the most impactful ENSO-warm phase in the instrumental era. The agricultural impacts across the tropics and subtropics, the rainfall deficits in southern Africa, the monsoon disruption in South Asia, the drought intensification in Australia would scale accordingly. The coral bleaching would continue and extend into reef systems that have not yet experienced mass mortality. The fishery disruptions would deepen. The atmospheric river seasons affecting the western United States would become more intense, delivering larger precipitation totals with higher flooding risk. The marine heat waves that have become the new normal in the northeast Pacific would intensify further, extending their impacts on the food web to depths and geographic areas not previously affected. This scenario is not a prediction. The Earth's climate system has variability, and forecasting the magnitude and timing of specific ENSO events more than 6 to 12 months in advance remains at the frontier of scientific capability. The heat content data does not tell us exactly when the next major El Niño will develop, or exactly how large it will be. What the data does constrain is the range of possible outcomes. The current subsurface heat content sets a floor under the next El Niño's sea surface temperature anomaly. A weak El Niño developing from the current state would still be warmer than a weak El Niño developing from a normal state. A strong El Niño developing from the current state would almost certainly produce sea surface temperature records that the current generation of climate models was not built to simulate. The Pacific is not going to cool back to the baseline of 10 years ago. The heat content increase is not reversible on any policy-relevant timescale. The trajectory of the Pacific heat engine has been altered by the cumulative uptake of heat from the warming atmosphere, and the system is now operating in a state that has no precedent in the observational record. This does not mean the future is known. It means the range of possible futures has shifted. The outcomes at the low end of the distribution, the mild El Niños, the modest droughts, the limited fishery impacts, are still possible. But the outcomes at the high end of the distribution, the record-breaking El Niños, the severe food security crises, the catastrophic coral mortality, have become more probable. The tail risks are fatter than they were 10 years ago, and they are fatter than the current generation of climate models fully captures. Let me give this a concrete geography. The simulation that concerns researchers most is not a global average temperature projection. It is a specific spatial pattern of sea surface temperature anomalies in the central and eastern equatorial Pacific that would develop if the next major El Niño draws down the current anomalous heat content fully. In that simulation, the Niño 3.4 index, the primary measure of El Niño intensity, reaches values in excess of 3 degrees Celsius above normal. No El Niño in the observational record has exceeded approximately 2.8 degrees Celsius in the Niño 3.4 index on a sustained basis. The 2015 to 2016 event peaked at approximately 2.6 degrees. At Niño 3.4 values exceeding 3 degrees, the atmospheric response is not a linear extension of what previous strong El Niños produced. The Walker circulation does not just weaken, it effectively reverses in some sectors. The rainfall anomalies over the tropics are not just shifted, they are dramatically amplified. The drought signal in southern Africa and South Asia is stronger than any El Niño in the historical record has produced. Whether the next major El Niño actually achieves these values depends on how much of the current subsurface heat content is accessed during the event's development phase, on the state of the trade wind system at the time of onset, and on a range of other factors that make El Niño forecasting inherently probabilistic. What is not probabilistic is the starting state. The heat is there, the subsurface profiles document it clearly. The question is only how much of it is expressed in the next ENSO warm event. The data that describes the Pacific's current thermal state, the Argo profiles, the buoy array readings, the satellite sea surface temperature analysis, is publicly available in near real time. You do not need institutional access. You do not need a scientific background, though it helps for interpreting what you see. You need a browser and knowledge of where to look. The first and most comprehensive real-time resource is the NOAA Coastwatch browser, accessible at coastwatch.pfeg.nooa.gov. This platform aggregates satellite-derived ocean data products into a map interface that allows you to visualize sea surface temperature, sea surface height anomaly, chlorophyll concentration, and other variables across the Pacific and other ocean basins. The most important product for understanding the current Pacific state is the GOES-SST, a daily composite sea surface temperature map derived from multiple satellite sensors. When you load the Pacific view of this product, you can immediately see the current pattern of temperature anomalies. Warm anomalies appear in orange and red tones, cool anomalies appear in blue. The current configuration, persistent warmth in the central and eastern equatorial Pacific, elevated temperatures in the western warm pool, anomalous warmth extending into the northeast Pacific is visible directly in the satellite data. The second critical resource is the NOAA Climate Prediction Center's ENSO page, accessible at cpc.ncap.noaa.gov. The CPC provides the official US government ENSO diagnostics and forecasts. Updated weekly with the oceanic Niña index, the 3-month running mean of sea surface temperature anomalies in the Niña 3.4 region of the equatorial Pacific, which is the primary measure of ENSO phase. The CPC also provides the ENSO outlook, which gives the probabilistic forecast for El Niño and La Niña conditions over the coming 12 months. Reading the Oceanic Niña Index time series tells you where the ENSO cycle is right now and how the current state compares to historical analogues. When the index is above 0.5 degrees Celsius, El Niño conditions are in effect. When it is below negative 0.5, La Niña conditions prevail. The duration and amplitude of each phase, visible in the historical time series, gives you the context for interpreting the current reading. The third resource is the Argo data itself, accessible through the Argo Information Center at argo.ucsd.edu. The Argo website provides float position maps, individual float profile data, and gridded data products derived from the full float array. For the Pacific, the most informative visualization is the heat content anomaly map, which shows the depth integrated temperature anomaly to 700 meters and to 2,000 meters across the basin. When you load the 2,000 meter heat content anomaly map for the Pacific and compare it to the historical record available through the same interface, the exceptional nature of the current state is immediately apparent. The warm anomalies in the equatorial Pacific and the western warm pool are not subtle variations around a normal baseline. They are large, coherent features that stand out clearly against the historical record. The fourth resource is the NOAA TAO project website at pml.gov/TAO, which provides real-time access to the TAO Triton buoy array data, the subsurface temperature plots, showing temperature at depth from the surface to 500 meters across the equatorial Pacific, are the most direct visualization of the thermocline structure and the subsurface heat content that we have discussed throughout this documentary. The key feature to look for in the TAO subsurface temperature plots is the depth anomaly of the 20-degree isotherm. The depth at which the temperature is 20 degrees Celsius, which is a proxy for the thermocline depth in the equatorial Pacific. When the 20-degree isotherm is deeper than normal in the eastern equatorial Pacific, warm water is building below the surface and El Niño conditions are developing or intensifying. When it is shallower than normal, cold upwelling conditions prevail. The current TAO plots show the 20-degree isotherm at depths that are anomalously deep across a broad area of the central and eastern equatorial Pacific, consistent with the subsurface warm water buildup that the Argo data shows and that we have discussed as the key concern for the next ENSO warm event. There is a fifth data resource that has become increasingly valuable for understanding the Pacific in near real time, and it is one that most people outside the research community have not heard of. It is the NOAA Global Ocean Monitoring and Observing Program's Ocean Heat Content Calculator, accessible through NOAA's National Centers for Environmental Information. This tool allows you to specify a geographic region and a time period and retrieve the depth-integrated heat content of the ocean for that region and period, derived from the Argo float data and earlier historical observations. It provides the number that we have been discussing throughout this documentary, not the sea surface temperature, which is what most public attention focuses on, but the total thermal energy in the water column to 2,000 meters depth. When you use this tool to look at the Pacific Ocean's heat content over the last 10 years and compare it to the full historical record going back to the 1950s, the acceleration of the last 3 years is immediately visible as a departure from the trend line that is qualitatively different from anything earlier in the record. This is the data that researchers are looking at when they say the Pacific is doing something it has never done before. Not the surface temperature map, which is striking but has been warm before in individual regions for short periods. The depth integrated heat content, which represents the full thermal loading of the water column, which has never been at this level across the Pacific Basin simultaneously. These four data resources, Coastwatch SST, CPC ENSO Diagnostics, Argo Heat Content Maps, and TAO Subsurface Temperature, together give you a complete picture of the Pacific's current thermal state. They update at frequencies ranging from daily to weekly and are free to access by anyone. The Pacific is telling its story in this data every day. The Pacific Ocean has been doing something unprecedented for the last 3 years, and the data accumulated by the Argo float network, the satellite instruments, and the NOAA buoy arrays makes it impossible to describe the current state as a temporary anomaly on the way back to normal. The normal is changing. The reservoir of heat in the Pacific water column is real. It is documented. It is not going to cool back to the baseline of a decade ago on any time scale relevant to decisions that people are making right now about water infrastructure, agricultural systems, fishery management, coastal development, and food security. This is not a statement about catastrophe. The Pacific Ocean has always been variable. El Niño and La Niña have always disrupted rainfall patterns and fisheries across the tropics. Communities around the Pacific have adapted to ENSO variability for thousands of years. The question is not whether adaptation is possible. Human communities are remarkably capable of adaptation. The question is whether the rate and magnitude of the change now underway is outpacing the adaptation capacity of the institutions and communities that depend on the Pacific's climate services. That question has different answers in different contexts. For the commercial fishing industry of the Pacific coast of North America, the adaptation requirement is urgent. Salmon populations cannot recover while the ocean they migrate through remains anomalously warm. Management frameworks designed for a cooler Pacific need to be redesigned for the Pacific that exists now. The species that can thrive in warmer water, Pacific sardines for example, which had been commercially extinct in the Northeast Pacific for decades before the blob, need to be managed for their potential role in a warmed system, not treated as anomalies. For the agricultural systems of the tropics and subtropics, Southern Africa, South Asia, Australia, the adaptation requirement is planning for the ENSO variability that the current Pacific state will produce. The historical record of El Niño impacts on rainfall provides a planning framework, but that framework needs to be updated for an El Niño signal that is amplified by the additional heat content of the current Pacific state. Drought preparedness that was calibrated for the 2015 to 2016 El Niño may be insufficient for an El Niño developing from the current starting conditions. For the countries and communities that depend on coral reef fisheries and tourism, from Australia to Indonesia to the Pacific Island states, the adaptation requirement is managing for a reef ecosystem that is under sustained thermal stress with no relief in sight. Reef management frameworks designed to allow recovery between bleaching events need to be revised for a thermal environment in which recovery intervals are shortening. For the engineers and planners who design water infrastructure, stormwater systems, and flood control along the Pacific coast of North America, the adaptation requirement is planning for atmospheric river events that are more intense than the historical record indicates, because the warm Pacific that energizes atmospheric rivers is warmer now than when most of the existing infrastructure was designed. These adaptations are not impossible. They require clear-eyed acknowledgement of what the Pacific data is showing. They require planning horizons that account for the trajectory of the Pacific's heat content, rather than assuming a return to historical baseline conditions that the data does not support. The Argo floats are out there right now, diving to 2,000 meters, ascending, transmitting their profiles to satellites overhead. The TAO buoys are measuring the subsurface temperature of the equatorial Pacific at this moment. The satellite passes every 90 minutes, imaging the sea surface temperature of the Pacific in swaths of data that accumulate into daily composite maps. The ocean is telling us what it is doing. It has been telling us for years, in increasing detail and with increasing urgency. The instruments are better than they have ever been. The data coverage is more complete than it has ever been. The physical understanding of the mechanisms driving the change is more robust than it has ever been. The gap is not between the science and the data. The science is producing the data. The gap is between the data and the decisions. Every institution that depends on the Pacific's behavior, from fishery managers to agricultural planning agencies, to water utilities, to insurance, actuaries, has access to the same Argo profiles, the same satellite SST maps, the same CPC ENSO diagnostics that we have discussed in this documentary. The question is whether those institutions are building those data streams into their planning assumptions in ways that account for the magnitude of what the data is showing. The Pacific is not returning to baseline. The heat in the water column is real and committed. The next major ENSO warm phase will develop from a starting state, unlike any previous El Niño in the observational record. The decisions that will determine how many people are adequately prepared for that event. How many communities have water storage? How many farmers have drought-resilient crop varieties? How many fishing communities have diversified their economic base are being made right now in planning cycles that extend 5, 10, 15 years forward. The data exists to make those decisions well. The Pacific is not hiding what it's doing. It is doing it in the data every day, visible to anyone who looks. The question has never been whether we can see it. The question is whether we choose to act on what we see. The Pacific has been giving us the answer to that question in stages. In 2013, it gave us the blob, a regional marine heat wave that collapsed the food web of the Northeast Pacific and told us that the ocean-atmosphere coupling could sustain anomalous conditions for years. The lesson was absorbed by the research community and partially absorbed by resource managers. In 2015, it gave us the worst coastal harmful algal bloom in recorded history, a coral bleaching event that killed large portions of the Great Barrier Reef and reef systems across the Pacific, and a salmon collapse that closed commercial fisheries along the Pacific coast. The lesson was absorbed more broadly. Fishery management frameworks were updated in some jurisdictions. Coastal monitoring was expanded. In 2019, it gave us Blob 2.0, a confirmation that the 2013 event was not a one-time anomaly. The lesson was noted. In 2023, it gave us a global oceanic temperature record that exceeded every model projection, a North Atlantic marine heat wave that the quality control algorithms thought was instrument error, and a set of Argo float profiles showing subsurface heat content at levels that had no precedent in the observational record. Each of these events has been a signal. Each signal has been clearer and more intense than the one before it. The data resolution has been improving continuously, making each signal easier to read. The institutional capacity to respond has been growing, making each signal more actionable than the one before. The Pacific is not done sending signals. The subsurface heat content documented by the Argo network in 2026 is the setup for the next signal, larger, more impactful, and more clearly connected to the accumulated trajectory of everything that came before. The people who will be in the best position when that signal arrives are the ones who read the current data clearly, who understand the mechanism, who have incorporated the Pacific's trajectory into their planning rather than their past. The Argo floats are diving right now. The data will be transmitted to shore by morning. The Pacific is telling us what it's doing. The question is whether we're listening. If this kind of deep mechanism-level analysis of what the Pacific is doing and why it matters is useful to you, the kind that takes the Argo data seriously and explains the physics behind the anomaly, subscribe now and turn on notifications. The next video in this series takes us inside the Argo program itself, how the floats are built, deployed, and maintained. What happens when a float transmits a reading that breaks the historical record, and what the scientists who read those records every day say about what the Pacific is telling them. In the comments below, after understanding the mechanism, the heat reservoir, the model failures, and the cascading consequences, which system do you think is most underprepared for what the Pacific is carrying right now? The fisheries, the agricultural systems, the water infrastructure, the insurance models? Your answer matters. This is the kind of analysis that shapes how communities prepare. Tell me what you see. If this deep dive into what the Pacific is actually doing is the kind of content you need, subscribe now, turn notifications on. The data updates every day, and so does this channel's analysis of it.